Okay, so let's do problem number 2 on exam number 3. This is the block of mass M1 initially at rest sliding down a frictionless ramp and then colliding with another block of mass M2 on the horizontal frictionless ramp. And we'll have different types of collisions we'll have to analyze. But the problem starts by asking you, well, what's the velocity of M1 just at the bottom of the ramp just before it hits M2? And this was meant to be a relatively easy question. It's actually based on material that was covered for the last exam. You should look at this and say, well, energy is conserved as that block slides down the ramp. Energy conserved because there are no external forces acting along the direction of motion, not taken into account with potential energy. E final equals E naught, with E final equal kinetic energy, 1/2 mv1 squared, assuming we define gravity's potential energy to be 0 at the bottom of the ramp, which then means that E naught equals m1gh, because it has the m1 has a potential energy of gravity of m1gh at the top of the ramp. So set those equal. 1/2 m1v1 squared equals m1gh. Solve for v, or v1, square root of 2gh. Done for part A. And now when we use V1 later, you can just use the symbol V1 instead of having to plug in the square root of 2gh everywhere. I wrote that in the exam statement just to make your life a little bit easier. Next question, what's the speed and the direction of each mass if the collision is completely inelastic? Well, the word completely inelastic tell you A, that energy is not conserved during the collision. And of course, momentum is always conserved during collisions because collisions are short, but completely inelastic furthermore means that the velocity is the same for both because they stick together after the collision. So momentum is conserved. We can use that. And we can use that V is the same after collision because they're sticking together. And I'll just define that as V final. That's the same V final for both masses. So now we write down momentum conservation. The initial is m1v1 momentum. It's all in the block 1 equals the final, which is the two masses stuck together. So they have a mass m1 plus m2 times v final. And you just solve that for v final. Write that as m1 v1 for m1 plus m2. Done. Okay, C. It says, what's the speed and direction of the center of mass of the system just before the collision? You can do this the hard way or the easy way, but let me do it first of all the easy way. The velocity of the center mass doesn't change due to the collision. And this is because the collision involves only internal forces, no external forces. And so there's no external forces to cause a change or an acceleration of the center of mass or a change in its velocity. So we know the velocity of the center of mass after the collision. We've just written it down. The two pieces are moving together, so they're also at the center of mass. So all I have to do is write that same answer again. Okay, velocity of the center of mass before just equals what I wrote down above. m1 v1 divided by m1 plus m2. Done. Okay. Now, if you want to do it the hard way, you could actually calculate the velocity of the center of mass and say, well, its velocity before the collision, there's mass 1 moving with m1 v1 plus block m2, but it's moving with 0 velocity. It's at rest, divided by the total mass. And you'll see this is the same thing as we wrote above there. It's not a lot more work, but it's a good, better to conceptually realize that you can just write this. Okay, that takes us to D. Part D says you have an elastic collision now and the masses are equal. And you must answer this question from basic principles of conservation of momentum energy. You are not allowed, it is strictly forbidden, to just use this formula that I worked out in lecture and Ohanian doesn't actually give you for generally for elastic collisions to write down an answer independent for any m1 and m2 and initial velocities v2 and v1 naught. You can't use that general purpose formula. You have to do this from basics. How do you do that? Well, you write down a momentum conservation relationship. P final equals P naught. Okay, remember all the masses are equal in this case, so let's just call them M, simplify our life. So mv1 final plus m2 v2 final. Actually, I'm sorry, just I won't write out m1 and m2. So mv1 final plus mv2 final. That's the momentum after the collision. The momentum before the collision was just mv1. Of course, the m's cancel out. And so I have what I'll call equation 1, v1 final plus v2 final equals v1. Now let's use energy conservation. This is momentum conservation if you want. So energy conservation says the final energy equals the initial energy, and we'll do something similar. I'll write out the final kinetic energy. Well, that's 1/2 mv1 final squared plus 1/2 mv2 final squared, or really it says m1 and m2, but they're the same masses. Okay, so that's the final kinetic energy of these. And it has to be equal to the initial, which is all contained in the first mass, 1/2 m1, but I won't bother with the 1, v1 squared. And I'll divide out the masses and the 1/2s. The 1/2s cancel, the masses cancel. I've got a second expression, v1 final squared plus v2 final squared equals v1 squared. So equation 1, equation 2. That's the physics of the problem. Now you're asked to just put on your math hat, take off your math shoes if you want, and solve these expressions for v1 final and v2 final. Now the problem also said it's only 1 point of algebra for that solution because it is math. It's not so much physics anymore. And there are lots of ways of doing that. So here's one method, and you may pick others. Square equation number 1. If you square equation number 1, okay, you'll get v1 final squared plus 2v1 final, v2 final, plus v2 final squared. Now that's equal to v1 squared, but we also have this expression for v1 squared. So this expression also has to equal that, v1 final squared plus v2 final squared. Okay, but notice I've got v1 final squared on both sides, cancel that out, v2 final squared on both sides, cancel that out. I have v2 final times v2 final has to equal to 0. Now I have to stop and think, well, what does that tell me? Well, they can't both be 0, or I'd have no energy at all. And energy has to be conserved. Is it possible for v2 final to be 0, but v1 final to be non-zero? No, because v1 can't move through v2. So the only way this could possibly be true is if v1 final equals 0. Well, if v1 final equals 0, I can go back to equation 1 up here, and I can say, if v1 final equals 0, then v2 final, we know is v1 minus v1 final, but that's 0, and so this is equal to v1. Okay, v2 final equals v1. So originally the second block was stopped, and the first block was moving in with velocity v1. After they hit, the first block is stopped, and the second one is moving off with the speed v1. And you were told to remember certain special cases like this. Okay, so that should give you some confidence if you did remember it. Okay. Now the other thing you could do if you wanted to is, now that you've got this answered, you could refer back to this expression, and you might say, well, v2 naught is 0, so these terms go away. What's v1 final? Well, just m minus m, because the masses are equal, so v1 final is 0. v2 final, what's that? Well, that's 2m divided by 2m, or just 1 times v1 naught. So v2 final equals v1 naught. So that would be a quick way to check your answer. The question does say you should in any case write down the correct final answer, and you could do that either from memory or because you went to that formula to get it. So even if you couldn't do the algebra, we expect it and assign credit to writing down this result. Okay, that leads us to E, the last part of this question. What's the speed and direction of each mass if the collision is elastic, but M1 is now much, much bigger than M2? And here I say that you can use the formula from the collision equation. I'm trying to conserve some time here. So we can use these expressions applied to the situation, but we still have V2 not equals 0. So I can write down the V1 final equals V1 naught times M1 minus M2 divided by M1 plus M2. Okay, and I can ignore this part of the expression, okay, because V2 naught equals 0. Well, in this case, okay, if M1 is much bigger than M2, then I can just ignore this and this compared to M1, and I have V1 final equals V1 naught. And this should make some sense. If you have M1 much bigger than M2 after the collision, it just keeps on moving with its original velocity, or something very close to it. Well, what do we get for V2 final? V2 final equals V1 naught times 2M1 divided by M1 plus M2. And remember, we ignored this second part of the expression again because V2 naught is 0. So if M1 is much bigger than M2 in this case, that tells us, well, just ignore that term. And then the M1s cancel, and so we have 2V1 naught. And you might remember from demonstrations and from analyzing this in the rest frame of V1 final that we found this in lecture also. So that's problem number 2.